I want to find the force exerted by this molecule when it hits this wall. Now, well, actually, you can imagine that when the molecule hits the wall, it bounces off. So it would seem that the force that it exerts on the wall only lasts for a very short time, during the very short time when it just touches the wall and bounces off. Okay, and then there will be no force until, well, after bouncing off, the molecule would move to the opposite wall. Okay, and it will bounce off that wall, and it will come back, maybe not along the same line, it's all very complicated. It might come back at another angle, and it would bounce off this wall again, and then this wall would receive another force for a very short time, and then the molecule will bounce, maybe like that, and come back and hit yet another part of this wall and give it another very short force, and then bounce off. Alright, so from this molecule, this wall would receive lots of forces for a very short time. Alright, it will receive a force for a very short time, and then a while later it will receive another force from the same molecule for a very short time. So the same molecule keeps hitting the wall and giving this short impulse, right? This impulse of a very short time. So what do we mean when I say I want to find a force? Right? Well, what I really mean is I don't really want to find that force, that very short force, when at the instant when the molecule hits the wall. Right? I have no idea how to find that. Okay, and I don't really need that either, because in the end we have so many molecules bouncing at the wall. We are not really interested in the force from a particular molecule at a particular instant in time. We are interested in an average effect. So we'll start by finding an average effect of this molecule, meaning that what I'm going to do is I'm going to imagine trying to find the average force over a period of time, and not just during the moment of contact. Okay, so this is how we're going to do it. Right. I'm going to think about what happens when I'm just going to follow the component of the speed along this direction. Okay, so this means I don't have to worry about bouncing at all sorts of different angles. So I'm just going to follow a motion just along this line. Now, when this mass, this molecule bounces off this wall, it will move in the opposite direction, also with the same speed u. Okay, the same speed u, but the direction is different. So there's a change in momentum, because momentum has direction. And then after bouncing and giving it a force for a short time, the molecule moves to the other wall, bounces back, come back and hit this wall again. Okay, so there is a change in momentum, right, each time it hits the wall. Now, and this change in momentum happens when it bounces, so it's just happen over a very short time, and then there is a relatively longer period of time when it's moving away, when there is no collision. So to find the average force, what I need is to simply take the change in momentum when it hits this wall, divided by the total time the molecule takes to go to the other wall and come back and hit again. All right. So although during this time there is no force in the wall, when we want to find the average, we have to divide by this total time. All right. We have to take the force that appeared for a short time during the bouncing, when the molecule hit the wall. We need to take that force and we need to average it over this duration where it go and come back. So therefore, we should find the change in momentum at the point where the molecule bounces off the wall, and divide it by the time t, which is the time taken for the molecule to go away and come back again. Right, when it comes back again, it will bounce again and cause the same force, and then it will go back and do that again. So what we need to do then is to consider what happens during a bounce and take the time between the bounce to do the averaging. So let's start. The force, therefore, let me try and calculate the force, would be the change in momentum divided by this time. So let me start by working out the change in momentum. Since I'm considering just motion along a line, I need to take a direction to be positive, either left, right, or left. So and as I've mentioned many times before, it doesn't matter which direction I choose. So I'm just going to choose the right hand side to be plus and the left hand side to be minus. So this gives the initial momentum, right, of these two velocities. So this velocity should have a plus sign, that velocity should have a minus sign. This one where after the bouncing. Okay, so the initial momentum therefore is m times positive u. So let me write that down. M times u with a positive sign. The final momentum would be after it has bounced, and it will be m times minus u. So there's a minus sign there. Minus mu. Okay. And I have to take the difference to find the change. So this change happened once every time the ball. Now between this change and the next change, the time is the time taken for the ball to go there and come back. What exactly is this time? Okay, let me try to find out. Now this time would surely be related to the velocity, right? And distance. Velocity is distance over time. So I need this distance. So let's say, well, if it is I have this box, then I can just take a ruler and measure it. But for now, let me just let this be L. Okay, maybe some number of centimeters. So let this be L. If I know that this is L, I can find the time, because let me write down the relation between the speed, the time, and the L. It should be the speed should be distance over time. So distance is go there and come back, so that's 2L. Right? That's 2L divided by time is what we want to find. Right? That's the time. This is the same time as here that we want to find for it to go there and come back. So okay, so therefore if I rearrange this, just exchange those two, I have 2L over U. And that's what I should divide here. 2L over U. So there we are. Okay, there we are. And therefore I can simplify this to, that's minus mu minus mu, that's minus 2mu minus 2mu, divide by this. So that means times, invert this, u over 2l. Now the 2 and the 2 cancels. So I have m u squared over l. So we are getting somewhere. Okay, we have this expression now. There is a minus sign there. So this minus sign tells us, what does the minus sign tell us? It tells us that the change in momentum is to the left. And the reason why the change in momentum is to the left is because this mass, this molecule, received the force from the wall in that direction. So when the molecule hits the wall, it experiences a force from the wall, and that's why it bounced back. Okay, so that's the sign. But we don't actually. But once we have obtained an expression for it, and we want to find the pressure, we don't actually need to know the sign. All right, if I just want the magnitude of the pressure. So let me write this out. So therefore pressure is equal to force over area, and that's the force. So mu squared over L divided by area. Okay. Divide by area. So this is equal to mu squared over LA. Now let's see what are L and A. L is this length, A is this area. So therefore this length times this area must be the volume of the box. So let me write this in terms of the volume, mu squared over the volume. Okay. Now let's not forget that the pressure here is the pressure from one molecule. It's not the pressure of the whole gas. Okay, it's just the one molecule. Now if I want the pressure for the whole gas, now before that, let me make a slight change here. In order not to confuse the P here with the pressure of the gas from all the molecules, I'm going to cross this out. I'm not going to use this symbol here. I'm just going to use the word from one molecule, comma, the pressure. Right? Just make it clear that this is the pressure just from one molecule. Now, then I'm going to write down the expression for pressure from the whole, from all molecules. Pressure from all molecules. So this is from all molecules. Now how do I find the pressure from all molecules? Right, all I need is to take this is from one molecule, and I can think of just multiplying by the total number of molecules. Okay, that sounds simple enough until we realize that we have a u there for the velocity of the molecules, and the velocity of the molecules are all different. They're all different. So so I can't just multiply by the number of molecules. Okay, I have to actually add up all the u squared of all the molecules. And of course, I can't do that because I don't even know the the velocity of one molecule. Okay, so we're stuck. Now, the way forward, is usually to think in terms of the averaged value of the molecules, the average value. So if I think about an averaged u squared, now average u squared is usually written in this form. Write this out. Average u squared is usually written as this bracket u squared, close bracket. Actually, it might also be written as u squared with a line on top. Okay, maybe I'll do that. It's there are fewer lines to draw. Okay, so if I think in terms of the average value for each molecule, then I can just say that when I total up all the u squared, it's the same as the total number of particles. Let's say n. N is the total number of oxygen molecules multiplied by the average value. Okay, so that would be the same that would be the same as adding up all the different u squared. Right, it would be the same as just taking n multiplying by the average value, assuming that I know what the average value is. But I actually don't yet. But let me just use this idea, right, to go forward. So in terms of the average of the velocity squared, okay, this is what I get after adding up all the u squared. So this would come from that part. Now those other parts are the same, right, because they are just constant factors. So I would have an m there, from there, and I would have a v. I would have a v for velocity for volume at the bottom. And finally, let me try to relate this to something more familiar. Now, m is the mass of one molecule. N is the total number of molecules. So if I take number times mass of one molecule, I should get the mass, the total mass of the gas. And so that's the total mass of the gas. And if I divide this total mass by volume, I should get the density. Okay, so we use rho to represent density, and that is still u squared averaged. So it now looks a lot simpler. Now let me write this out here. So I'm saying that m times n is the total mass, right? That's the mass of one molecule, total number of molecules, and big M would be the total mass of the whole lot, the total mass. And V there is the volume. It's the volume here. Okay, so I'm saying that the density must be the mass, total mass of the gas divided by the volume, and the mass must be mass of each molecule times the total number of molecules. Okay, so this is where it comes from. All right, when I say Nm over V, this is the same. Okay, so we can see that this is actually the density of the gas, which is the rho here.